Now let's take a look at practice question set number 30. I told you guys yesterday that you can expect on your unit test coming up next Tuesday to have a decay curve, a radioactive decay curve on the first page. It's question number 1. And that decay curve is going to look something like this. We don't know what it's going to say on the y-axis, whether it's percent, whether it's grams, whether it's kilograms, whether it's just a number, whatever, it doesn't matter. It's going to be n. Okay, the amount remaining on the y-axis, and it's going to be time on the x-axis, and the shape of it's going to look like this. We know that in order to analyze one of these questions, we're going to go either up and over or over and down. Okay, let's see what the question asks us here. It says the time required for a 40-gram sample to decay to 1.25 grams. Let's figure out what the half-life is. Okay, let's figure out what the half-life is. We start with 100%. How much is left after one half-life? Statistically, at least. 50. So we go 50 over and down, and we would say that that is. Be careful with the divisions on the axes. Sometimes we don't quite read the question carefully enough. We don't quite determine what the divisions are carefully enough. We look at, sometimes 0.1, 0.2, whatever. Be careful here. It goes 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So the half-life would be 0.6 hours. Okay, 0.6 hours. Now, how many half-lives do we have? Well, we want the time that's required to go from 40 grams to 1.25 grams. I'm going to do the old divide by 2 method. Some of you might use logarithms for this, right? We're going to say after 0 half-lives, we've got 40 grams. 1 half-life, it's 20 grams. 2 half-lives, it's 10 grams. 3, it's 5. 4, it's 2.5. And 5, it's 1.25. So we've got 5 half-lives. We want to find what T is. We're going to say it's 5 times 0.6, which is 3.0 hours. Make sense? Yes? Anybody do it a little bit differently? Because there is kind of another way to do this one. Just look at the graph. Well, be careful. What you don't want to do is like go 1.25 and go over and down. What you could say, go ahead, Braden. Okay, and you got what percent? Okay, good. So now you've got 3.125% remains. So then you could go over and down from 3.125%, right? The danger of that is that it's kind of hard to tell exactly where 3.125% is, right? Okay, and especially as a numerical response, there's a little bit of danger in that, but it works. Okay, in theory that works. All right, next question. Multiple choice number 1 says medical diagnosis patient may be injected with this isotope. Isotope has a half-life of 6 hours, decays to a stable isotope by gamma ray emission. That doesn't sound good. That doesn't sound good. But you got to remember that it's such a small amount that they're injecting into you. We're exposed to all kinds of ionizing radiation all the time. And if they expose you to a little bit more, then that's okay. You don't want to be exposed to too much more, right? But a little bit more is okay. It says, if the biological processes that might eliminate some of the technetium-99 from the body are ignored, the maximum percentage of this that could be present after 24 hours is what? 24 hours would be 4 half-lives, right? 4 half-lives. So we're going to say n is equal to n0 1/2 to the little n. We've got, what's our initial amount here? 100%. 1/2 to the 4 gives me, do the math there, it works out to be 6.25. 6.25%. Well, this is from our last unit as well, number 2. It just happens to go with that information. We want to find the wavelength of this. All we're going to do is say E is equal to hc over lambda. Remember this? Remember this? Lambda is equal to hc over E. We're going to make our E 3.85 times 10 to the 6 eV, because it's megaelectron volts. What are you going to make H? Planck's constant 4.14, though, times 10 to the negative 15 eV times seconds. Now, how many people converted that to joules? Anybody? Okay. If in doubt, use joules, right? Go joules or go home. Okay, we know that joules will work here. You just got to be consistent here, but you're also allowed in this case to use the electron volts. Either way, you're going to get an answer of B, 3.23. And finally, number 3, says an experiment starts with 1.45 kilograms. After 32.2 days, 90.6 grams are left. What's the half-life of iodine 131? We want to find T1 half. To find T1 half, we're going to say N is equal to T over T1 half. T1 half is equal to T over N. So this is 32.2 days divided by, we don't know what N is. You want to find N by the other equation. You can use logs, right? Or we can use the divide by 2 method. After 0 half-lives, we've got, let's do grams here, okay? After 0 half-lives, we've got 1,450 grams. That's what we start with. After 1 half-life, we've got 725 grams. After 2 half-lives, it's 362.5 grams. After 3 half-lives, it's 181.25 grams. After 4 half-lives, it's, oh, look at that, 90.6 grams. It's actually like 90.625, but we're pretty darn close there, right? So little n is 4. 32.2 divided by 4 gives me 8.05 days. So my answer is C.